The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, thank you for coming to the second part of our session on use of high-strength concrete and high-strength steel in reinforced concrete columns. And our first speaker is Jeff Rautenberg, and he got his PhD from Purdue University recently, and he's a design engineer at Janney Elstner, and he's going to talk about seismic response of building structures reinforced with high-strength steel. Thank you.
Good afternoon. Thanks everybody for showing up. If I do one thing successfully today, it's make this title a little bit more interesting. What I want to do is talk about high-strength steel, but specifically some numerical models that we did to look at the response of building structures using high-strength steel. So the title is Numerical Estimates of the Seismic Response of Building Structures Reinforced with High-Strength Steel. A long title, but I'll get started with a definition just right off the bat. So when I talk about high-strength steel, I'll compare it to standard grade 60 steel with just this simple plot. Here's an idealization for 60 KSI steel. Everybody's seen this. I sort of just chopped off the strain hardening part, but just an idealization. But if I compare that to what I'm calling high-strength steel, we see, as you might expect, the more rounded behavior, no flat yield plateau, not as high, and I guess many people define it different ways. But if you use the 0.2% offset method, you get around for this stress strain curve, we get about 120 KSI. For the yield stress. For the high-strength steel that I'll be talking about, I'm referring to steel with a rupture strain better than 7%. Now that's not quite as good as standard A706 grade 60 steel, which is going to be a 15% or so. But it's still it's not so bad. I'm sure all of you at one time or another have seen a picture like this. I'm not quite sure what this guy's thinking, but I know he's not happy, or maybe he is happy. Maybe this is one of the laborers that gets an extra year of overtime out of this. But you can see it's really artful how they built this. It's an unbelievable amount of steel. How much steel they put in there. There's vertical bars, horizontal bars. You can't see them, but there's 90-degree hooks, 135-degree hooks. There's headed bars in there. Absolutely everything. Coupled bars. It's really, really incredible that they even built that. I guess it's good that they got practice because they need to again. I'm not quite sure how they fix that, but I don't know. And so, obviously, there are tons of advantages that everybody in the past session and in part one of the session and part two of the session are going to be talking about. But a few of them are. Obviously, you have the potential to reduce congestion of the steel. Use higher strength steel, you need fewer bars or smaller bars. It's fairly obvious. You reduce shipping costs. If you need half as much steel, you need half as many trucks to bring that steel to the job site. If you have half as much steel, you need half as much installation cost, essentially. So you can really save a lot of money. The steel does cost a little bit more. Last time I looked, it was sort of proportional to the yield stress of the steel. So essentially you're paying for a force. So 120 KSI steel was about twice as much as 60 KSI steel. But once you factor in the shipping costs and the installation costs, then it really turns into be a pretty decent savings for a good-sized job. And finally, you reduce your environmental footprint. You produce less steel, less mining, less material costs. But with everything, there are disadvantages. This is a photo from a test that I did a couple of years ago. This isn't, and so this is a column that's reinforced with high-strength steel. And what you can notice, this is after I tested it and after I chipped out all the loose concrete. These longitudinal bars, they're buckled, which isn't necessarily the end of the world. But if you're using fewer bars or if you're using smaller bars, in combination with a higher stress demand on those bars, the likelihood of them buckling is higher than when using a traditional grade 60 bar. I sort of mentioned this before, but there's a lower fracture strain of the high-strength steel. For a column that, if you don't push your steel all the way to fracture, then it really doesn't matter a whole lot. For the test that I'll sort of briefly mention, we fractured, I think, 1 or 2 bars in the specimens. Everything else was relatively ductile, more of a buckling type failure of the bars after very large drifts. And finally, what I'm going to talk about most today is the reduced post-cracking stiffness that you get out of a section that's reinforced with high-strength steel. As you might imagine, and what I've been saying is that you can use less of it, but as we all know, that the bending stiffness of a concrete member is proportional to the transformed moment of inertia, right? So if you use less steel, there's a lower crack moment of inertia means a softer bending response. And so I put up this sort of cheesy graphic because I'm going to sort of talk about what the effects of using high-strength steel are. But I'm going to start sort of on a cross-sectional level, and then I'll zoom out and zoom out and zoom out, and finally get to an entire frame, models of a whole frame. So to start with a sectional response, if I take two column sections, both same dimensions, both same concrete strength, both the same amount of applied axial load. These, for this little exercise, I applied 20% of F prime CAG. But in the section on the left, I have a reinforcement ratio of, say, 2% based on the gross cross-sectional area, but using 60 KSI steel. The section on the right, I use half as much steel, 1.5%, or whatever I said, 2 to 1 or 3 to 1.5, whatever it was, half as much steel, but twice as strong. And if I look at the moment curvature response, this is what I see. So for the regular, the column reinforced with standard 60 KSI steel, we see what we might expect. Pre-cracking behavior right here, after cracking but before yield, and then we start yielding the bars in tension up here. If I do the same exercise with the other cross section, this is what I get. And so before cracking, we get essentially the same behavior because the gross cross section controls. After cracking, we get a softer response because of that transform moment of inertia, and then we start yielding up in here. There's a few things that you should notice about this. One, obviously, is it's softer after cracking. The secant stiffness to yield, the effective secant stiffness is less in the column reinforced with high-strength steel. But what's also important is that even though you're using less steel, you essentially get to the same moment capacity, and you essentially get to the same curvature capacity. This is at a limiting concrete strain of 0.04, I think. So I didn't artificially cut these off at the same spot. They both reach the same limiting curvature, and that's important. So if we sort of zoom out a little bit, we can look at what happens on a member response. If this behavior is sort of fed up the food chain to the member, the full member. And I looked at this during my stint at Purdue with tests. And so here's just one photo of one of the tests. And so these are columns that I tested. And I apply an axial load with this external post-tensioning system. And then I apply a reversing lateral load in this direction. increasing magnitudes. We get a hysteretic behavior of this column. And so I'm going to show you two plots. One is for a column reinforced with grade 60 steel, like the plot that I just showed you. And the other one is using half as much steel, but high strength. And so this is what we see for the column with 60 KSI steel. Nice, fat loops like we might expect. And by the way, these columns have 20% F prime CAG, so it's nothing to scoff at. And they have the shear stress that they're subjected to is on the order of 6 roots of F prime C. So it's pretty highly stressed in shear. And they ended up getting out, this column ended up having a drift capacity of around 4%. We ended up buckling some of the longitudinal bars here, but really stable loops, to 4%, even further. If I compare that to a comparable column with half as much steel, but 120 KSI, this is what we see. Skinnier loops, softer initial stiffness, but we see essentially the same drift capacity, around 4 or 5%. So still pretty good. We ended up buckling a bar in compression here, and then reloaded the other side and buckled a bar in compression on the other side. And so we idealized this for our later computer analyses with these hysteresis models. The white one being a column reinforced with 60 KSI, the red being reinforced with 120 KSI. And really there's two main differences here. Both stem from the same the same thing. It's the difference in post-cracking stiffness. And so here's essentially the secant stiffness to yield for the grade 60 steel column. And here's the secant stiffness that we assumed for the other one. And for the analyses that I'll talk about, we essentially assumed that the stiffness was half. And so because that stiffness was half, then we ended up getting these thinner hysteresis loops dissipating less and less energy, or less energy than the grade 60 KSI column. So let's zoom back again and start talking about what we see sort of not on a member basis, but sort of beyond that on a frame response. What we want to know is, is this change in stiffness, does that result in an increase in drift demand in an earthquake? Is it higher? Probably, if off the top of your head. How much higher? I could argue that it's one possibility is it's 41% higher, or root 2. If we change the stiffness by half, T equals the square root of K over M, you end up with the possibility of having 41% higher drift demand. And so we'll start looking at, and so for a linear elastic system, this really happens to be the case, but not necessarily for low periods. For low periods, if I come into my spectral displacement period plot and look at a given period and a given displacement, and then double that, or increase that period by 40%, which is square root of 2, I end up getting up to 100% more drift. Again, that's for a linear elastic case. If I look at a longer period, say 1 second, that's that 41% that I was mentioning, the square root of 2. So for a linear elastic case, we could really expect to get about 40% extra drift. But I want to look at now what happens in a nonlinear case. And so myself, in collaboration with other researchers, did nonlinear time history responses of single degree of freedom systems that had elastoplastic behavior. Again, changing the stiffness by 2. And this is what we see. Let me take a minute to explain this plot, I guess, because it's kind of difficult to understand. But basically, we're comparing the displacement of a system that we assume is reinforced with 60 KSI steel to the maximum displacement of a specimen reinforced with high strength steel. So points lying above this line of unity means that the drift is higher in the specimen using high strength steel. And for this case, we see that the average is 28%, which, and I guess for the case of this presentation, I'll call that the high strength steel penalty, because you're penalized 28% in drift by using high strength steel. But that's just a single degree of freedom system. As we start moving up further and further, we'll look at a multi-degree of freedom system. And this was really the heart of the paper, is that we modeled 4 different frames, one 3-story, one 6-story, one 12, and one 20, and we modeled it 2 ways. In one of them, we assumed that all beams and all columns had grade 60 steel. In the other, we assumed that all beams and all columns had grade 120 KSI steel. And we shook them in the computer with 7 ground motions. And this is supposed to look like spaghetti because it's just showing that, you know, we used a wide array of ground motions, large differences in frequency content, large differences in amplitude, and we subjected all these to nonlinear time histories and looked at the results. And this is a plot that's similar to the one that I showed you before, but this is for these multiple degree of freedom systems. And again, points lying below this line of unity means the drift in the buildings with conventional steel was less than the drift in the buildings with high strength steel, and vice versa. And what we see is this. And so the average here is essentially 15% of a drift penalty in it for using high strength steel for a multiple degree of freedom system. And so the penalty decreased as the number of members increased, right? You're in the single degree of freedom system, you end up with a 28% drift or high strength steel penalty. But now more members are participating, more members are cracking, more members are yielding. It's shifting around that nonlinearity to more than just one member. And so the penalty is a lot less. If we take this a step further and look at what everybody uses the term hybrid now, so I figured I would use it also. I modeled a hybrid building in that the columns I assumed were using high strength steel, but the beams were conventional steel. And so a well-proportioned building, we know that you want to proportion it so that the columns are stronger than the beams. And so really that pushes a lot of the nonlinearity into the beams. The columns really should stay, they'll crack a little bit, but they're not supposed to yield. That's by design. That's how we do it. And so by keeping the beams with 60 KSI steel, then you still keep the stiffness, the stiffness of the members that are working as they were before. And this is the result. Same plot as before. Points above mean higher drift for the high strength steel buildings, and the drift penalty drops to 3%. That's really nothing. I mean, for as much as we know about estimating the response of buildings to seismic motions, it's really a trivial amount. Even the 15% is essentially trivial. So it really shows a lot of promise that you can use high strength steel in these buildings and not see a huge effect on drift demand of the building. And so to summarize sort of what I talked about, this is what we see from the 4 different types of analyses I mentioned. With a linear elastic system, we see a penalty of about 41%, square root of 2. If we start introducing nonlinearity into the single degree of freedom systems, that drops to 28%. As we increase the number of members, we further drop to 15%. And then if we force all that nonlinearity into members that still have 60 KSI steel, it all but disappears. And it's pretty interesting. And so to summarize, I just have a few conclusions. One of them is that for a multi-degree of freedom system with all the members reinforced with high strength steel, you use half as much steel. It takes much less energy to build. It takes much less material to build, a lot less steel. And you really only end up with 15% extra drift demand. In addition to that, sort of a subpoint is that as you increase the number of stories, that sort of the penalty decreases. But what's, I think, very important is that all of these are just numbers on paper. They really need to be looked at through a real, physical tests. Actual building models need to be shaken with these high-strength steels to see what the actual behavior is. And so with that, I'll finish and ask if anybody has questions.
Any questions for Jeff?
Rautenberg, I may have missed something.
Sure.
Could I see the plot for the hybrid case? That's the one?
That's the one, yeah. Yep.
Are there deviations on the order of 30%? Individual?
Yeah, so I sort of mentioned this at the very end, but as you increase in number of members, the penalty decreases. So it's hard to steal it's hard to see because I stole this from elsewhere, but these points here are the 3-story buildings, so they have the fewest members. As we start getting into the taller buildings, the 6 and the 12 and the 20 stories, those deviations really are reduced. And so my contention would be that you're less likely to use high-strength steel even in a 3-story building because you're not going to get a lot of congestion. As you get higher into taller and taller buildings, that's when the congestion issue really comes into play. And so, these points don't really matter so much. Well,
all right. Thank you very much.